And if you have any question, you can raise your hand and I'll try to answer. Okay. So, Bismillahirrahmanirrahim. In our last class, we started our discussion on probabilities. We discussed about joint probabilities. That is, from that we learned about joint distribution, then marginal distribution, and we concluded our discussion with conditional probabilities. All right. So continuing with that thing, in addition to conditional probabilities, which so far have been numbers, we have conditional distributions. So they are basically a vector of numbers that describe the probability of various outcomes that sum to 1, except these outcomes are conditioned on an event. Okay, so here we have a joint distribution table, the same one as we saw before. Using this, we can compute the probability distribution over W given the evidence T equals to half. Okay, so this is what we have. This is what we want to calculate. Okay, first of all, whenever we have a capital letter here, the W here, or it indicates that it's going to be a distribution, right? So at a data structure level, we can think of this as an array in that dimension. So when we see, let's say, P of capital W, we are considering an array of probability values, considering all the values that W can take. Okay, so there is going to be an entry for the sun and an entry for the rain, because these are the only two values that W can take. All right, and each one of them is going to be, let's say, P of sun given hot and P of rain given hot. Here, hot is the evidence. All right. So let us, if I try to compute them, we got 0.8 and 0.2. Let's try to figure out how we got them. All right. So for P of sun given hot, it should be equal to the joint distribution divided by the marginal distribution, right? So the joint distribution is P of sun and hot divided by P of hot. Okay. So P of sun and hot can be derived from the table, that is this one. Okay, that gives us 0.4 divided by P of hot. So it's not directly given, but we have to look at all the evidences where the temperature is hot. So that is the first row and the second row. So if we sum up the probabilities, we get 0.5 divided by, 0.4 divided by 0.5, which is 4 by 5, or 0.8 as shown in the table. Okay, so similarly, we can also calculate for the rain, right? You can do it on your own. So this is called the conditional distribution. Here, the conditional distribution is based on the weather, which has the evidence that, okay, the temperature is hot. Okay, there can be other conditional distributions as well. Let's say P of W given T is equal to cold. All right. So understand that this is not a marginal distribution. So what would have marginal distribution would have been look like? So P of W, let's say we have sun and we have rain. So if we calculate the marginal distribution for the P of W equals to sun, then we get the consistent rows, that is the first row, the third row, that gives us 0.6. And for the rain, we have 0.4, right? Okay. So we can look at this and say that before we had any evidence, that is the marginal distribution, if someone asked us what is the probability or what is the chances that the sun will rise today, we will see the sun in the sky, we would have said there's a 60% chance, right? But if that person tells us that, okay, it's hot weather, okay, the weather is hot now, the temperature is hot, then what happens? Then they ask me that, okay, since the temperature is hot, now tell me, what is the probability that if I look at the sky, I will see the sun? So you will see that the posterior probability conditioned on the evidence goes up to 0.8, okay, 80%. So there is a high chance of having a sunny day. And that sort of makes sense, right? So whenever we have a hot weather, a hot temperature, we can say that, okay, there's a high probability that it's a sunny day. Okay, so mathematically what we are doing here makes sense in the real world as well. Okay. So basically, we are getting qualitative changes in variables of interest, like what's the weather. And that change as a function, that change is a function of an evidence that we get. Okay. And this very change is definitely related to the joint distribution, right? Which sort of has everything. Okay. And so our belief gets updated based on the evidence that we get. Okay. And this is exactly what we do in probabilistic modeling. We built a joint distribution and we asked that, okay, we have this evidence and that evidence, tell us about certain particular variable. Okay. So as we get more evidence, our beliefs should change in this manner. Okay. So updating our beliefs in a well-founded way is what we do mostly in probabilistic reasoning. Okay. So I hope this one is clear to everyone. Let us move on to normalization trick. So one thing that we do a lot in probabilistic reasoning is to calculate the conditional distribution. Okay. In particular, we usually want the whole distribution, right? So let's say we are given certain evidence and we have the huge joint table. From that, we want to calculate some conditional distribution over some variable. Okay. So for example, uh, we do not really care about how likely it is for a ghost to be in a certain place in the grid work, right? So in the entire grid, for a particular grid position, we do not care about that. Instead, we want to know the probability distribution of the ghost being in all the positions. Okay, for a particular position, if we know that okay, there's a low chance that this cell does not contain a ghost, we might avoid this. But if we get the whole distribution for the entire grid, we can simply consider that okay, among all the probabilities that indicate that how likely it is that the ghost is there, we will simply take the maximum, right? That will give us a square and we will pass there. Okay. So usually we want a conditional distribution over our query variable, given the specific evidence that we have. In the case of Ghostbuster, the specific evidences that we have are the sensor readings, albeit noisy, that we can work with that. But our query variable is how likely it is that the ghost is in the square, right? And we want to calculate it for all the squares. And based on that, we want to make a decision. Okay. So usually we will have this joint distribution table containing the entire grid for the entire grid, and we will take the maximum and we will be done with it. Okay, fine. So usually whenever we are calculating conditional distributions, we will start with the joint distribution table that will contain the variables that we care about, and there will be some other variables that are evidences. Okay, and we will have some query. We want to know something. Okay, we want to know the probabilities, let's say, of the weather outcomes given we know that the temperature is cold, something like this one. All right. So how do we compute that? So let us try to do it formally. So we compute that using the definitions of conditional probability. First, we calculate the probability of sun given. So to calculate the distribution, we consider that, okay, fine. What is the probability that the weather will be sunny given the temperature is cold? That is equal to this one. So that is basically, sorry. So the numerator is basically the probability of having the weather sunny and the temperature being cold. That can be directly derived from the table. That is cold and sunny. That is this row, 0.2. Okay. And the denominator contains the probability of the temperature being equal to cold. Okay. So if we expand upon it for the denominator, we get something that looks like this, right? The probability that the weather is sunny and the temperature is cold, plus the probability that weather is rainy and the temperature is cold, right? Okay, so that gives us the value 0.4, something that looks like it. Okay, so here, notice that in the, again, as I said in the last class, in the numerator, we have this thing, and in the denominator, we also have the same thing and something else. All right, so keep this one in mind. So with that in mind, let us try to calculate the rain condition. So probability that the weather is rainy given the temperature is cold. So if we expand upon it using the formula, we get something that looks like this. So this is the joint distribution of weather being rainy and the temperature being cold divided by the probability of the temperature being cold. That is the marginal distribution over cold temperature. So if we expand on it, we get something that looks like this and we calculate the value. Okay. Again, notice what we have in the numerator, we have this thing, and in the denominator, we have this thing again, and something else. All right. So using the definition of the conditional probability, we can calculate both of them. Right. Now, notice that when we expand it, the two formula, this one and this one, are almost similar, right? So the numerator is different, but the denominator is the same. That means for the first one, we have, let's say, rain and cold. Sorry, for the second one, we have rain and cold. For the first one, we have sunny and cold. And both of them are divided by the same thing. Okay. And that very same thing is basically the summation of the two numerators that we have in two different equations. Okay. So this numerator and this numerator summed up gets divided here. Right. And that is the key of normalization trick. Whenever we are calculating these conditional probabilities, we divide them by the total probabilities corresponding to the sum of all the numerators. Okay. And the benefit is that we can simplify this thing then. Okay. So how do we simplify? Here's the algorithm. Okay. So the input to our algorithm will be a joint distribution table. All right. Let's say someone has asked us to calculate the probability distribution over the variable w given t is equal to 4. Okay. So rather than trying to think about which row corresponds to what, we are going to think about this like a table operation in the database. Okay. So we have this huge table containing lots of rows and columns. Okay. The first operation that we do is the select operation. Okay. We say that we will select the rows that match our evidence. Okay. So the evidence here is that the temperature is cold. So we will select only the third and fourth row here to get a much smaller table. Okay. So here, what we have is we only have the entries that are consistent with the evidence that we are given. Okay. So now consider this thing that what is the summation of the probabilities of the original table? It's 0 0.4, 0 0.1, 0 0.2, 0 0.3. It sums up to 1. Okay. So it's a well-formed normalized probability distribution. But whenever we selected some of the rows here, what does it add up to now? It's not 1 because we took some of the rows out from the original table. And the stuff that got ejected were part of what summed up to 1. Okay. So what we are looking at here is a sort of a distribution over W for our evidence, except they don't add up to 1 anymore. Okay. So that is why we write this one as P of lowercase c, comma W. Okay. So the next operation is to make sure that they sum up to 1. And to do that, we use this operation called normalize. Okay. So the way the normalization works is we keep their proportions for each of the entries and we divide them by their sums. Okay. So the summation of the probability in this middle table is 0 0.5. So we take each of the entries and divide them by 0 0.5 to get 0 0.4 and 0 0.6. Okay. So the thing that we are dividing with is basically the same quantity that kept showing up in the denominator that we saw earlier. Okay. Is this clear to everyone? Any questions so far?
So then why are you dividing by the denominator? You can just ignore it, right?
Sorry, louder.
I say in that case, you can just ignore the denominator while calculating.
No, we want the conditional distribution, right? So to get the conditional distribution, we have to make them sum up to 1, right?
Right.
That is why we are dividing. Okay.
Yes, sir.
All right. Okay. So we have some probability distribution now that sums up to 1. Okay. How do we know that this is the conditional probability of W given T equals to C? Well, consider that whenever we are selecting that give us the right numerators. Okay. When we perform the select operation that matches our evidence, that is basically selecting the numerators. And then whenever we normalize them, that gave us the correct denominators. All right. So adding up the cold and sun and cold and rain gave us the probability of cold. Okay. So the total there is going to be the probability of C, which is the denominator that we are looking for. Okay. So to compute conditional probability, we do two operations, that is select, and the second operation is normalize. Okay. And the reason that we want to do this thing is, I don't know whether you have done big data or similar courses or not. You'll see that these table operations are much faster compared to your regular summation and collection operation. Okay, if you consider regular mathematical operations where we use a bunch of formulas, compared to that, these table operations are faster. Why? Because we can consider this one that we have a big data system where we will simply use the MapReduce. Have you heard of the MapReduce algorithm? Some of you at least. Those
Yes,
who
sir.
are doing data mining warehousing, MapReduce. So if you haven't, no problem. You can see it in the future, inshallah. But the basic idea here is that whenever we have these sort of table operations, that is select operation and normalize operation, which basically sums up and divides. So these sort of operations can be done in parallel. Okay, and they can be made much faster compared to your regular calculations. Okay, so here the speed up is not obvious for this small table, but for a huge table, you see that we can make it very fast. Okay, by simply using MapReduce, and there are even faster algorithms to do it. Okay, so let us do a quiz to understand that we have understood the normalization trick or not. So here we have the joint distribution with probability with variables x and y. So we will try to compute the conditional probability of x where we have the evidence that y is false. Okay, the evidence is y is false. Now we have to calculate the conditional distribution. So raise your hand if you can answer. I will help inshallah, no problem. So the first question is, whenever we have this joint distribution table, we will perform the select operation. Yes, ID 230. Which rows should we select? 230.
So for minus y,
Yes.
like given that it's y equals to minus y, it should be for the denominator second and the fourth row, like 0.3
Second
plus
row, second row and fourth row. So
yeah,
we are not
point.
thinking about numerator or denominator. We are thinking the rows that match our evidence, right?
Yes, sir.
Yes. So the evidence is minus y. So we will select the rows that contain minus y, right? So 0.3 and
Yes.
0.1. Thank you. ID 230, right? 30. Okay, good. So 0.3 and 0.1. We have selected that row. So now the next thing is we have to normalize. So someone else raise your hand. ID 242. You already raised your hand.
Sir, we have to divide it by the summation of
The summation of the probabilities. What is the summation? What do they sum up to?
0.4.
0.4. So if we divide both of them by 0.4, we get 3 by 4 and 1 by 4. That is basically 0.75 and 0.25. Thank you. ID 242. Okay, fine. So this is the conditional distribution that tells us that, okay, fine, given, and you can see that they sum up to 1, that given y is false, the probability that x is true is now 75%. Previously it was 30%. Sorry, previously it was, let's say, given y is false, there were some other evidences. Now we have 75% chance that now x will be true. Okay. Fine. So an additional question here. Let's calculate the marginal distribution. Okay. Sorry. Not P of W, P of X. So somewhere else, marginal distribution over P of X for X plus and X minus. Raise your hand. Anyone? Raise your hand. No one? I will help inshallah, no problem. 230 already answered. Someone else. Yes. 105.
Assalamu alaikum, sir.
Walaikum
Sir,
assalam.
for plus x, it should be 0.5.
0.5. How?
So
Considering which
0.2
row?
plus first two rows.
First two rows. 0.5. So minus x should also be
0.5.
0.5. Right. Thank you. ID 105. You should not be in this section's class, but you are.
Sir,
No
I
problem.
wouldn't be able to attend the class at 2:30 p.m. That's
Okay, no
why
problem. It's fine. All right. As long as you're attending classes, that's good. Okay, thank you. 105. So what do we have here? For the marginal distribution, we have 0.5 for plus x and 0.5 for minus x. So previously, whenever we did not have any evidences, we could say that the probability that the x will be true is 50%. Okay, there's a 50% chance, but given y is false, now the values have changed, right? Our beliefs have changed. Okay, so we had marginal probability distribution given no evidence, and this is the conditional one given y is false. You can also calculate for y is true, and for x is false, x is true, and so on and so on. Okay. So to formalize, the dictionary definition of the term normalize is to bring or restore to a stable or normal condition. Okay. So that happy normal condition that we are looking for here for the probability is the sum to oneness. Okay. So we had our joint distributions, they summed up to 1. We removed some rows, they do not sum up to 1 anymore, so we normalize them and they are happy. Okay. So we have talked about the entire procedure in detail. There are lots of other examples that you can see here, and you can do it on your own if you want to. Okay. So here, one interesting thing here is this one, example 2. So you notice that the values are 25, 10, 50. What do they mean? Can anyone tell me? 50. So they sum up to 50. Okay. So basically, this is how we calculate the joint distributions. All right. So what we will do is each day, let's say we wake up at 10 a.m. and then we look outside, we see that what is the weather condition? It's sunny or it's rainy, and whether the temperature is hot or cold. I have, let's say, made some distinctions binary. Okay. And we record them. All right. So after 50 days, we see that, okay, 20 days, we got hot and sunny weather. 5 days, we got hot and rainy weather, and so on and so forth. Now to get the joint distribution table, we simply normalize it by calculating the z value, that is the summation over all the entries, and that gives us this huge joint distribution table containing the probabilities for all the possible outcomes. Okay. Fine. Moving on. So this is the core part of this week's lecture, that is probabilistic inference. Okay. So probabilistic inference is when we compute a probability that we want. Okay. Like where the ghost is given by evidence, or let's say what is the probability of this heart condition given the test results. All right. Or let's say how likely this email is a spam given there are a certain bunch of words in it. Okay. So we are computing our desired probabilities that we don't know until we compute it using the probabilities that we do. Okay. So for example, we have the joint probabilities, but we want to know the conditions. All right. So how do we do that? We will select some rows, we add a few things, we normalize, and so on and so forth. Another example can be, let's say we have one conditional and we want to compute another. Okay. That will be using something called a Bayes rule, which we will talk about in a bit. Okay. But in general, probabilistic inference is basically going from a set of known probabilities to the desired probabilities. Usually they are conditional probabilities. For example, let's say we might be curious about in our model, let's say when we are driving to IoT, how likely is it that we will reach on time given there are no accidents? Okay. Maybe we can do some computation over the joint distribution to find that, okay, it's 90%. Okay. That will represent the agent's belief given the evidence. Okay. So the rational agent will have beliefs that correspond to conditional probabilities. That means we will consider that the probability, what is the conditional probability over the variables that I'm interested in given the evidence. Okay. And as we get new evidence, our beliefs can change. Okay. So the probability that we are on time given no accidents might occur 90% of the time. But let's say if we are driving at 5 a.m. in the morning, we are starting from our home very early, it's more likely that there will not be any traffic jam, and it's more likely that we will be on time, right? But let's say if it's raining, then it might be less likely, right? So observing new evidences causes our beliefs to update. Okay, and that is the important part of designing a rational agent. Okay, that is the basic idea. So in the general case of computing a quantity from a joint distribution is an algorithm called inference by enumeration. Okay, it's an exponentially slow algorithm. Okay, operating on an exponentially large table, so it's not going to be tractable. but the algorithms that we want to learn is that are going to be tractable are based upon this one. Okay, and you will see that they are doing the same computation but in some efficient way. Okay, so we are going to do the inefficient thing to build our intuition so that in future, whenever we learn about the efficient algorithms, we understand what is going on there. Okay, so in general case, we will have a whole bunch of variables. Okay, and we will have a joint probability distribution over that. Okay, again, it's exponential in the number of variables. Now, from this very large table, we are going to have our evidence. So the evidence variables are E1 and through EK. Okay, these evidences have values. Okay, so let's say we know that it's raining, we know whether the lights are on, we know what is the test result, and so on and so forth. Then we have this query variable. Sometimes there might be multiple variables, but often there is one, and that is the variable that we want to know. Okay, for example, given all these information about the weather, the temperature, and whatnot, do we need an umbrella whenever we are going out? Okay, given all these information about the sensor readings, where are the ghosts? Okay, that is the query variable. Okay, so we want a distribution over the thing that we don't know given what we do. Okay, so we want to compute the probability of the query given all the evidences that we have. All right. There's another class of variables that these are variables that we don't know, so they are not evidence variables, and we also do not care about them, so they are not query variables as well. Okay, these are called hidden variables. All right, so for example, in the Ghostbusters case, the sensor's value at a position that we haven't sensed yet is a hidden variable. We don't want it as a part of our answer, but we don't know it either. Okay, right? So we divide our variables in three categories. Evidence variables are the things that we know. Query variables, the things that we want to know. Okay, the things that we're interested in. And the hidden variable is the things that we do not care about and also do not know. Okay, so how do we run this algorithm? There are going to be 3 steps. Step 1, we'll select the entries that are consistent with our evidence. We have already done this in the small place. So we cross out lots of entries, and all that matters are the entries that match our evidence. Okay, so if we know that it's raining and it's hot, we cross everything that is not raining or not hot. Okay, then we sum out all the hidden variables. Okay, we take away all those variables that we don't want. Okay, and we get rid of those dimensions in our multidimensional array. All right, so how? We get rid of them one column at a time, and for each one, we sum together all the rows that now appear to be the same because they are only varied on that particular, axis, and we got rid of. Okay, the way this happens is that whenever when we get the distribution, we have the value for the Q given all the values of the H and the specific values of the E. Okay, we then sum over all the values of H, and everything that collapses together gives us a smaller table. Okay, and the last step is to normalize. Okay, so we take the whole distribution, select what's consistent with our evidence, collapse the variables that we do not care about, we'll be left with an one-dimensional array, which is our query, and we will normalize. Okay, so the algorithm might seem complicated. Let's do an example to understand it clearly. Okay, consider that you have this umbrella room, okay, or an AI assistant that might consider the season, the temperature, and the weather conditions to decide whether to give you an umbrella. Okay, so the first question, what is P of W? Okay, this is the query which also happens to be a marginal distribution because there is no evidence. Okay, so since we do not have any evidence, the whole table is consistent with our observations. Okay, so we cannot cross out any rows. So the first step is skipped. Okay, but we can still collapse on the S and T. Okay, because they are not observed, they are not part of the query, they are hidden variables now. Okay, so what we are going to get will look like this. So P of sun and P of rain. All right, so for the sun, we are going to find out which rows are going to collapse together. So the rows that have the entry sun. Okay. Okay, so sun, 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 sun. So if we sum them up, it should sum up to 0.65, all right? And for rain, the remaining values, which should be 0.35, okay? So that is the probability of sun and rain given there is no evidence, all right? What about normalizing? So you'll see that adding these two values sum up to 1. Okay, so we have the original values, and this makes sense since we did not cross out any rows, so we do not need to normalize. Or you can simply think of it like this, that okay, if we sum the entire thing, we get 1, and if I divide both of the values by 1, we get the same thing as before. All right? Fine. So we have this joint distribution table now, or marginal distribution, you can call it, that given low evidence, there's 35% chance of raining. So our agent might decide to skip on the umbrella. Okay, it might say that, okay, we don't need an umbrella. Okay, now next question. So if someone says that, okay, fine, it's winter, all right, our robot has found out that it's winter season going on. So what is the probability distribution of W given the evidence that it's winter? Okay, so to calculate that, what do? We're going to cross out all the rows that are inconsistent. So we are going to cross out all the summers, right? So that is this one, this one, this one, and this one. So we have these 4 rows now. Okay. So we are left with a smaller table, which is consistent with our evidence. Now, we still only care about P of W. So we need to collapse this one as well. Okay. You'll see that after crossing out the seasons, for the season 1, we have single value. Now we are concerned about the weather, so we will collapse these rows as well. Okay. So how do we collapse? Again, we are going to have P of sun given winter and P of rain given winter. Okay, we are going to calculate that. So what is the P of sun given winter? That will be the collapsed rows, that is this one and this one. So if we collapse them, we get 0.25. Then P of rain given winter, that is this row and this row, that gives us 0.25 as well. Okay. So now we are going to normalize them by dividing them by the sum of the entries. So each of the entries 0.25, 0.25. If we sum them up, we get 0.5. If we divide both of them by 0.5, this is what we get. Okay. So what happened here? Previously, without any evidence, we thought that there's a 35% chance of having rain. Okay. But somebody said to us that, okay, it's winter. So our beliefs are updated. And we said that, okay, now there's a 50% chance that it will rain. Okay. So that makes us a good rational agents. All right. The last one, the probability distribution of W when it's winter and hot. Okay. Given that it's winter and it's the temperature is hot. So what do? The step 1, we select the rows that are consistent. So we will erase the inconsistent rows. That is this one, this one, this one, this one, this one, and this one. Okay. So we are left with 2 rows where the other hidden variables, so the other variables, there are no other hidden variables. So we are left with 2 rows. So we get P of sun given winter and hot and P of rain given winter and hot equals to 0. For the sun, we get 0.1. For the rain, we get 0.05. Okay. Then we don't have to collapse anything since we do not have any other hidden variables. So we are left with this one. Then we need to normalize things. So if we normalize, we get 0.666 for the sunny and 0.333 for the rainy. Okay. So how the numbers go up and down, it will depend on the specific numbers in the joint distribution, but the computations that lead to them, I hope you can now see a formal structure. Okay. So if the quantities given on the joint distribution table is correct, the computation that you do and the values that you get should give you a rational agent. Okay. So if there is any question regarding how we do inference by enumeration, you can ask. Anyone? Alright.
So I understand
Yes.
the processing, but you are saying hidden
Mhm.
variable.
Yes.
What's the hidden variable?
Hidden variable is a variable that we do not care about. Okay.
Okay.
So, for example, whenever we are calculating P of weather given winter, all right. So we crossed out these 4 rows, right? We do not bother about them, right? Okay.
Okay. So the variables are S, T, and W, right?
Yes, yes. So now here, S is same for all the variables. That is our evidence, right?
Yes, sir.
Okay. Then W is what we care about, right? We want
Yes,
to
sir.
know what is the probability of sunny and rainy. So now we have this temperature variable that we do not care about. Okay, we do not know what is the temperature condition for this probability, do we?
No.
Right? So we don't know, and we also do not care whether it's hot or cold, right? So this is a hidden value,
Okay, sir, I understand.
right? And we collapse the hidden value. Thank you for the question. So I hope now everyone gets an idea about inference by enumeration. Moving on to problems with inference by enumeration. There are some subtle problems and there are some obvious problems. So the obvious problems are simple. You can see that the worst case complexity will be big of d to the power n because the table can be huge and we need to store the entire joint distribution table. So space complexity is big of d to the power n, right? There are some subtle problems as well. Okay. One of the problems might be that we might not have the entire joint distribution to begin with. Okay. Once we get the joint distribution, getting down to the query is really easy. However, consider the amount of computation or amount of things that we have to do to learn all the probabilities. Okay. We need to see an exponential amount of evidences as well. All right. Let's say day-to-day data, we have to track it for the weather, season, and temperature for, let's say, thousands of days before we can come to a conclusion that, okay, this is a joint distribution table that we can work with. Okay. So somehow this giant table of everything is not going to work. Okay. So the idea is that we have to build this big table out of the little pieces that you can actually compute and store efficiently. Okay. Up to now, we have been talking about tools that let us take this big joint distribution table and shrink it. But now we need to know some more tools that will help us convert one thing to another and merge things so that we can take the small things and make the huge joint distribution table. Or let's say completely skip calculating the joint distribution table and get to the query. Okay. All right. So let us try to do that. You have already seen these things. So we can't have inference by enumeration if we don't have joint distribution. And sometimes what happens is that we might have the conditional distribution, but we want the joint distribution. Okay. So to calculate that, we use something called a product rule. Okay. So we have our marginal distribution of y itself. Okay. And we know that how x behaves conditioned on y. So from the definition of the conditional probability, if we multiply both sides by probability of y, we can get the joint distribution. Okay. How does that work? So let's say this, we have this example. So let's say somebody comes up to you and gives you these two tables. All right. So it says that we know that it's sunny 80% of the time. We know that it's rainy 20% of the time. Okay. So this is a marginal distribution. Then we have the second table. It's not a conditional distribution, by the entire table. Can anyone tell me why it's not a conditional distribution? Anyone?
So it does not add up, it's not normalized?
Yes, it's not normalized, right? So what is this? So we have these top two rows, if you can see, they add up to 1. And the bottom two rows, they add up to 1. Okay. So they are basically two conditional distributions stitched together. All right. That is what we have here. And you can see that the first one has the condition, the weather is sunny. And for the second one has the condition that the weather is rainy. Okay. So they are a family of conditional distributions on the weather. Okay. So if I want to calculate the joint distribution, we can use the product rule here. Okay. So let's say we want to find the probability of wet and sunny. Okay. So we have the sunny weather here, and we have wet given sunny here. So if we multiply these two, we will get the probability of wet and sunny. Okay. Then if we want the probability of dry and sunny, let me mark things. So if we want to figure out this one, dry and sunny, so what do we need to do? We need to take the sunny, that means probability y, and dry given sunny, and multiply these two to get, let's say, 0.72. Okay, something like this. And in this way, we can calculate the other values as well. All right. So this is the product rule. And the generalization of the product rule is the chain rule. Okay. So it says that if we want to have the joint distribution over any number of variables, we can build it using this formula. We can take the marginal distribution of the first variable, then we can multiply it with, let's say, x2 given x1, and then we can multiply it with x3 given x1 and x2 for 3 variables. Okay, to get the probability of x1 and x2 and x3. Okay, and we can keep doing this until we have all of them. Okay, this is the generalized formula. Now, why does it work? So what do we have here is this one, right? We know this one from the product rule formula. All right, probability of x2 and x2 and x1 is probability of x1 multiplied by probability of x2 given x1. And if I expand this one using the base rule, what do we get? Sorry, no, not the base rule, product rule. What do we get? We get probability of x2 given x1 divided by probability of x1. These two cancels out, and we end up with probability of x2 and x1. Okay, and we can expand it for 3 variables as well. So probability of, let's say, x3, x2, and x1 is basically probability of x3 multiplied by probability of what do we get? Okay, so let's do it in this way. So if we have this thing, which is probability of x1, now if we multiply probability of x1 with probability of x2 given x1, multiply it with probability of x3 given x2 comma x1. Okay. So we will have something that looks like this. So this one turns out to be probability of x2 and x1, okay, which gets multiplied here. We have, we will have probability of, for this one, x3, x2, and x1 divided by probability of x2 comma x1. These two cancel out to give us the probability of x3, x2, and x1. Okay. So you can simply expand upon it as much as you want. All right. So if we have the correct sequence, the first variable, the second variable given the first, the third variable given the first and second, and so on and so forth, we can determine the joint distribution. All right. That is our chain. So one more thing that we need to learn is the Bayes rule, and this is the famous rule of probabilistic inference, but it's just a consequence of what we already know. Okay. So the idea is that whenever we want to calculate the joint distribution, there are 2 ways to do it. All right. So if I want to calculate probability of x, and y, that is basically probability of x given y multiplied by probability of y, or we can calculate probability of y given x multiplied by probability of x. Okay. So this is the result from the product rule. All right. Now, if we divide both the sides of this equation with p of y, we get something that looks like this. Okay. So p of x given y is just p of y given x times p of x divided by p of y. Okay. So this helps us calculate one conditional probability from other conditional probability. Okay. So the way I like to think of it is like this. So we have P of X given Y. If we multiply P of X with it, we get the original joint distribution of P of X and Y. And then if we divide it by P of Y, we get back the conditional distribution of X given Y. Okay. This is also known as the Bayes rule. Okay. Now, question is, why is this helpful? So often what happens is that you sometimes have one conditional distribution, but not the other. Okay. So Bayes rule helps you convert that. Using this, you can flip the condition around, and this helps because generally one of the conditionals are easy to model, and we can model it and flip it to get the other. Okay. So for example, let's say if you're running a clinic, it's really easy to compute the probability of a person being alcoholic given they have liver disease. How do we do that? You will simply count the number of patients that got admitted with liver disease, and you will ask them, all of them, that are you alcoholic or not? Okay, and based on that, you can get a probability. Let's say 100 patients were admitted with liver disease, and let's say 60 of them were alcoholic. So you can say that the probability that someone is alcoholic, given they have liver disease, is 60%. Okay. So now if I want to find out if a person has liver disease given they are alcoholic, it's difficult, right? In general case, it's difficult. Given certain person says, given a patient comes that, okay, I am alcoholic, do I have a liver disease or not? How do I calculate the probability? It's not that easy, right? So what we can do is we can use the Bayes rule, and we can simply convert alcoholic given liver disease to liver disease given alcoholic and get the probability. Okay. And you'll see eventually, inshallah, one day, that Bayes rule is one of the most fundamental equations of artificial intelligence. Okay. So let us do a simple example to understand how it works. Okay. So we want to consider the diagnostic probability from causal probability. All right. So what is the idea? We want to find out the probability of cause given effect by using the Bayes rule. All right. So that is basically saying something like this. So let's say a patient comes to you, you're the doctor, and says that, okay, sir, I have this, and this symptoms. Okay, I have this problems. You run a bunch of tests and you see a bunch of results. From that, you want to determine whether that particular person has a particular disease or not. Okay. Now, what is the probability that this person has this disease, right? So you want to calculate that. But it's difficult to calculate. So you take the help of Bayes rule. All right. And we will do it with an example. So let's say a patient comes to us and they say that, okay, I have a stiff neck. Okay. And one of the symptoms of meningitis is stiff neck. All right. So a person came to you and they are telling you that, okay, doctor, I have stiff neck. Now you want to diagnose that whether that person has meningitis or not. Okay. So the cause here is meningitis and the effect is the stiff neck. All right. So now we would like to know that the probability of meningitis given the patient has a stiff neck. Okay. So if that is directly given in a medical textbook, we are happy. But if we don't have that, then it will be difficult for us, right? So if we have some fragments of probabilities that look like this, we can probably do some computations. Okay. So what sort of computations can we do? We can know a few things. So for example, we can know the total number of patients that got admitted and have meningitis. Okay. So basically we will do a statistical analysis. We'll see that, okay, in this hospital, how many patients got admitted and how many of them have meningitis. So let's say, considering the total number of patients that got admitted, let's say 0.01% of them have meningitis. Okay, that's a reasonable fact that you could know. Okay, then from studies of people who have meningitis, we can also identify how many of them have stiff neck. Okay, so let's say we have 100 people, or let's say 1,000 people diagnosed with meningitis, and we can ask them, do you have stiff neck? And let's say 800 of them replied that, okay, I have stiff neck, right? So from there, we can say that, okay, 80% of the time, people who have, given they have meningitis, also have stiff neck. Okay. So we might also know that how often a general stiff neck occurs, okay, in people who usually do not have meningitis, all right? So that might be this probability, okay? given a certain person did not have meningitis, they were diagnosed with non-meningitis patients, and we can ask them that, okay, do you have stiff neck or not? And if they have stiff neck, we can count that as well, and that will probably be a small number. Okay. All right. So now another, so from that, what we can do is we can use our Bayes rule. Okay. So someone told us that given I have a stiff neck, what is the probability that I have meningitis? Okay. How do we calculate that? We use the Bayes rule and we expand upon it, and we get the probability that given a person has stiff neck, what is the probability that person has a meningitis? And as it turns out, the number is very small. Okay, so it's like a meteor that does not really happen that much. All right. Okay, so that is one point. That is how Bayes rule can help us diagnose a patient. Okay. Now, another point to note here is definitely if you have a stiff neck, you'd still probably want to get checked. Okay. Why? Even though the probability is small, you still want to get checked. All right. Why is that the case? So it's not that the probability is really high and Bayes rule is wrong. It's not like that. It's because you are a rational agent, and it's because a utility. Okay. So if you have meningitis and you do not get it checked, that's really bad, right? So even though it's unlikely that you have meningitis, given that you have stiff neck, you want to maximize your utility. Okay. Always remember that maximizing the utility is not the same as the most likely outcome. Okay. All right. So considering the utility of getting checked and not having meningitis is probably higher, right? So that is why, even though the probability is small, you might decide that, okay, I need to get checked. Okay. So if you have stiff neck, get it checked. All right. Okay, so I hope this example made things clear about how we can use Bayes rule to get diagnostic probability from causal probability. All right, this is an important concept that might be useful in the exam. We'll see. All right. So there's a quiz here which you can do to test yourself. Okay. So let's revisit our Ghostbusters scenario. So let's get back to where we started, right? So we will have some assumptions regarding where the ghost is. That is called our prior distribution. And we know how the sensor works, which we know given each possible distance, how likely the colors are. So given that and the biases rule, we can compute the posterior probability over the ghost locations given the readings. Okay. So let us see that in action. Where is it? My bad. Okay. All right. So here's the Ghostbusters again, and this is our current belief distribution on where the ghost is. Okay, we don't exactly know where the ghost is, so we see that each square is equally likely. All right. So what happens is each time we will take a reading and our beliefs will get updated. All right. So a green reading, a sweep of low probability surrounded. Okay. We will continue taking measurements. Let's skip a bit. Okay. So if we keep taking the measurements yellow, then we will continue. Let's see here, some more, here and there, and you see that this cell is becoming very likely, right? The posterior probability is basically narrowing things down, and there's a 100% chance there's a ghost here. So we take the bust action and we get a hit, right? Okay. So this is what video games are like with probabilities. All right. So I hope you can see how useful it is to be able to compute in a precise and well-founded way your uncertain evidence in order to figure out your beliefs over the query variables. All right. And we can use a bunch of things that we have done throughout the way: inference by enumeration, base rule, product rule, chain rule, conditional distribution, marginal distribution, joint distribution, to calculate all of these things. All right. So with that, we are done with today's class. If you have any questions, you can ask me. Any questions? So if there are no more questions, then we are done, alhamdulillah. So hopefully I will visit my office tomorrow, inshallah, and I will try to check as much script as possible, given the time permits. The mid scripts, I have not completed checking them yet. So within tomorrow or the day after tomorrow, I will hopefully call you and show you your script, and I will give you some time. And regarding the final exam, the syllabus is up to this chapter, probability. So we will have to study it. I haven't set the question yet. Again, I will try to set the question by tonight, inshallah. And once I set the question, I will post the entire syllabus in the Google Classroom. And at the same time, I will mention whether you can skip any chapter or not before mid or after mid. Okay. Hopefully there will be more questions leaning after mid, but after mid we could not cover that much. So I have to lean on to before mid as well. So we'll see. Okay. Again, as I said, if there's any chapter that you can skip, after setting the question, if I find any, I will let you know, inshallah. Okay. So that will be all. Keep preparing for the final exams. It's the first exam, right? On December 5th. Is it?